Hi everyone and welcome back to the Morse Coders. Our today's topic is number system and base conversions. This is a very important topic for your academic as well as your competitive examinations. Today in number system we'll be covering decimal to binary conversions and binary to decimal conversions. So we need to understand what is a number system. A number system is a way of writing numbers. So it is a unique representation of writing numbers when we have a certain set of symbols and rules. So you can understand it in the form of any language. So whenever you were taught any language in your childhood, say you were taught to write English, you were made to learn what does its alphabet means, right? So in the similar way, we need to understand well, what are the symbols and the rules that are uniquely used to represent that number system. In order to represent a number system, what do we need? We need a base or a radix. Okay, and what are the applications of these number systems? It can be used in mathematics, sciences, engineering, as well as in computer science. So there are very different types of number systems available. The very first being the decimal system with the base 10. So it is the commonly used number system that you know till today, that you are using till today. So that is with the base 10. So that means that every number in this world could be represented with the numbers from 0 to 9. So whatever is the base of the number system, so here in this case it is 10. Base is also called the radix. The numbers it can represent would be -1. So that means 10 minus 1 is 9. So it can represent the numbers from 0 to 9. And it is the most commonly used number system which you use in your day-to-day life problems. The second number system is binary number system, which is very useful in digital electronics and in the era of computers. It uses only two digits. That means that everything can be represented either in an off state or in an on state. So the number system with base 2 is known as binary system. Then we'll understand the octal system. Octa means 8. So that means the number system with base 8 is the octal system, and it can represent digits from 0 to 7. It is also a commonly used number system in case of computers. The last one we have is hexadecimal. So hexa means 6 and decimal means 10, right? So that means it is the base for this number system is 16. And the digits it represent is 0 to 9. That means 0 to 9 is decimal. And A to F means up till 15. So that means your A becomes your 10. Your B becomes your 11. Right? Your C, it becomes your 12. D becomes your 13, E becomes 14 and F becomes your 15. So that means whenever in an hexadecimal number system you need to represent 10, what you would be writing? You would be writing A in place of that. So that is why a hexadecimal number system represents the digits from 0 to 9 and A to F. That means 0 to F, that is 0 to 15. It is also used in computers and it is used to represent some large numbers with very fewer digits. The next topic we need to cover is decimal to binary conversion. So whenever you are given a question to convert a decimal number into a binary number, you need to follow these steps. So here a number 253 is given with 10 written on its base, right? So that means that this number is in decimal form. We need to convert it to binary number. We know that binary number contains only ones and zeros, right? So how would you do that? For that, you will basically be taking the form of an LCM. You will write the number, whatever you need to convert from decimal to binary here. And since you need to convert it into binary number system, we would write its base here. That is 2 here. So what you do is you need to divide this number by 2. That means, so when you divide 253 by 2, you get 2 ones are 2, 2 twos are 4, you have 1 remainder and 2 six are 12. So that means since it was an odd number, okay, you will always have 1 as remainder, right? And whenever it is an even number, you will always have 0 as a remainder. So you will continue dividing this number by 2 step by step until you get a 0 remainder, okay? So if you have 126 here, you repeatedly divide it by 2. Then you have 63 in the quotient and 0 in the remainder, right? So when you divide 63, it is an odd number, so you would have 1 as remainder. Similarly, when you divide 31 by 2, you have 15 as quotient and 1 as remainder. And you would continue this series of steps until you have a 0 remainder, right? So when you are done dividing this decimal number by 2, you now need to find its binary equivalent. So what you need to do is, since I have placed this arrow from bottom to top, you need to start writing these digits in the same format. So that means that this number over here, it becomes your least significant bit. And this number over here at the bottom, it becomes your MSB or your most significant bit. If you do not understand what a least significant bit is, so it is the number that comes to the rightmost section or the rightmost part of your number. So here in this case, this one at the rightmost corner is your least significant bit, and this one on the leftmost section is your most significant bit. So what you do is, from bottom to top, you just write this number. So that is 1, 1, 1, 1, 1. So these are 6 ones over here. So these are 6 ones over here. Then it's a 0 and it's a 1. So this is your binary equivalent of 253 in decimal form. The next part is understanding the conversion of a fractional decimal number into its binary equivalent. So say for example, we have 0.45 here in decimal form, and it needs to be converted into its binary equivalent. So what we do is, in that case, we write the number and we multiply the fractional part by 2. So that means 0.45 over here is multiplied by 2. It becomes 0.90. And in this case, what is done is, the integral part is taken and written separately. So we write the 0 over here. Integral part means the part that comes before the decimal. And the part after the decimal, it is taken and it is repeatedly multiplied by 2. So in this case, 0.90 again is multiplied to the response of 1.80. Again, we separate the integral part, that is, we take 1 here and we multiply the remaining part, that is 0.80 into 2. This 1, 2, 3 over here denotes nothing but the sequence of steps. We continue to do this until we get the response as 0 or we get a repeated response. So you see that we repeatedly multiply the numbers here again by 2 until we got a repetition, that is 1.60 over here was repeated. So in that case, we stop the process, and what we do is, instead of going from bottom to top, we go here from top to bottom and write the equivalent. So in this case, the equivalent becomes 0. So the number here before the decimal would be the part that we learned before, that was simple decimal to binary conversion by repeatedly dividing the number by 2 if we have any, and just in case we have it like simply like 0.45, then the next part after the decimal would become by writing these numbers from top to bottom, that is 0, 1, 1, 1, 00. So this would be the binary equivalent of 0.45. Hope you understood this concept. So now if we go through these steps, it will help you understand better. So in order to convert a decimal number into a binary number system, what you need to do is, you need to repeatedly divide the decimal number by 2, and it will give you certain result with respect to a remainder. In case the number is even, right, then we get 0 as a remainder. In case the number is odd, we were getting 1 as remainder, right? So when we place all the remainders in order from, our least significant bit would come at the top and our most significant bit would come at the bottom. So that means we would write those numbers from bottom to top. It would give you your required number in binary format. And for fractional parts, we saw that we would multiply the fractional part repeatedly by 2 and place the digits from top to bottom. That is, your most significant bit over here becomes the number that comes at the top, and the least significant bit over here becomes the number that comes at the bottom. The next we have is binary to decimal number conversion, right? So here we have a number 1010.01 with the base 2, which denotes that this is a binary number and it needs to be converted to decimal number. So what we do is we follow these steps. So let me write this number over here again, though I've already solved the example, but I'll solve step by step for you. So it's 1010 point and then say a 0 and a 1, right? So what we do is we start with the powers of 2. That is, the first number to the left of decimal is multiplied with 2 raised to the power 0. The next number is multiplied with the subsequent increasing power. That is, 1 over here is multiplied with 2 raised to the power 1. The further next number is again multiplied with the increasing power. So in this case it would be 2 raised to power 2. And this number over here, which is the last number, which is to the extreme left, would be multiplied with the next power, that is 2 raised to power 3. Had we had another number over here, it would have been multiplied with 2 raised to power 4, right? And then we place an addition operation between all these. As far as the numbers to the right of the decimal are concerned, that is the fractional part, what we do is we start with the negative powers. So we already have 0. So what we do is we multiply this number by 2 raised to the power minus 1. And this next number with the 2 raised to the power minus 2. And then place an addition sign in between these. Now we need to solve this. So 2 raised to power 0 is 1. Anything raised to power 0 is 1. And when it is multiplied by 0, it is 0, right? So let me place a 0 here. Then we have 2 raised to power 1, that is 2, and multiplied by 2. So 2 ones are 2, right? Then again we have this number 2 raised to power 2 multiplied by 0. Let me clearly write a 0 here. And then we have 2 raised to power 3, that is 2 twos are 4, 4 twos are 8. It gives me an 8. Let me write an 8 here. To the right of decimal, here this number is being multiplied by 0, so I'll clearly write a 0 here. And then we have 2 raised to the power minus 2. I hope you know how to solve minus powers. So it becomes 1 by 2 raised to the power 2. So that means the negative power goes to the base and it becomes 1 by 4 here, right? So when we solve this further, we have 8 plus 2, that is 10. We place the fractional part as such, that is point over here. And 1 by 4 is 0.25, right? So let me write a 25 here. So this becomes the decimal equivalent of the binary number that was given to us. And this is something similar we have performed in these steps above. So what we have done is we have taken the increasing positive powers of 2 for the non-fractional part and the increasing or rather decreasing fractional powers for the fractional part of 2, and then we further perform these operations. So now if we go through these steps, it becomes quite simple. So that is, in order to convert from binary to decimal number, we need to multiply the exponent or the power of 2 with each digit of the number in decreasing order. So if we go to the left hand side of the fractional part, it is the increasing order of the powers, and if we see the other way around, it is the decreasing order of the powers, right? And for the fractional part, we do nothing but divide it by the power of 2. So for example, if you had 2 raised to power minus 2, just like in last case, it would be something equivalent to 1 by 2 raised to the power 2, right? Hope you've grabbed the concept. Thank you everyone for tuning in today. Do not forget to like, share and subscribe our YouTube channel, The Morse Coders. Until next time, happy coding.